বক্তৃতানুষ্ঠানত উপস্থিত থকা আটাইকে 15 মিনিট শিক্ষাৰ তৰফৰ পৰা আদৰণি জনাইছো। বিগত এবছৰ আমাৰ এই অনলাইন শিক্ষা মঞ্চৰ জৰিয়তে শিক্ষাৰ্থীসকলৰ বিশেষকৈ স্নাতক মহলাৰ শিক্ষাৰ্থীসকলে জানিব লগা বিভিন্ন বিষয়ৰ বুনিয়াদী ধাৰণা অথবা তত্ত্বৰ আলোচনা, বিভিন্ন বিষয় অধ্যয়ন কৰি গ্ৰহণ কৰিব পৰা বৃত্তিৰ সা-সুবিধা আৰু আমাৰ মুলুকৰ সৰুবৰ বিভিন্ন স্থানৰ পৰা ওলাই আহি শৈক্ষিক আৰু বৃত্তিগত জীৱনত সফলতা লাভ কৰা শিক্ষাৰ্থীৰ জীৱনৰ বৰ্ণিল যাত্ৰাৰ কাহিনী আগবঢ়োৱাৰ প্ৰয়াস কৰি আহিছো। আজিৰ অনুষ্ঠানত আমাৰ মাজত উপস্থিত আছে ভাৰতীয় বিজ্ঞান শিক্ষা আৰু গৱেষণা প্ৰতিষ্ঠান তিৰুভানন্তপুৰমৰ চমুকৈ IISER ত্ৰিবান্দ্ৰমৰ পদাৰ্থ বিজ্ঞান বিভাগৰ সহকাৰী অধ্যাপক ডক্টৰ অমল মেধি। তেখেতে ইতিমধ্যে কোৱান্টাম পদাৰ্থ বিজ্ঞানৰ ওপৰত দুটা বক্তৃতা প্ৰদান কৰিছে, সেয়ে তেখেতক পুনৰ পৰিচয় কৰি দিয়াৰ বিশেষ প্ৰয়োজন নাই। বৰ্তমান বৰপেটা জিলাৰ বনগাঁৱত জন্মগ্ৰহণ কৰা ডক্টৰ মেধিয়ে এটা বৰ্ণিল শৈক্ষিক যাত্ৰাৰে গৈ আজিৰ পৰ্যায়ত উপনীত হৈছেগৈ। এই বক্তৃতাটো একে সময়তে জুম, ইউটিউব আৰু ফেচবুকৰ জৰিয়তে সম্প্ৰচাৰ কৰা হ'ব। শিক্ষাৰ্থীসকলে তেওঁলোকৰ প্ৰশ্নসমূহ চেট বা কমেন্ট বক্সত লিখি দিব পাৰিব। আমাৰ মডাৰেটৰসকলে তাৰ পৰা প্ৰশ্ন লৈ আমাৰ বক্তালৈ আগবঢ়াই দিব। জুমত উপস্থিত থকা শিক্ষাৰ্থীসকলে পোনপটীয়াকৈ প্ৰশ্ন সুধিব পাৰিব। বক্তৃতা চলি থকা সময়ত অংশগ্ৰহণকাৰীসকলক নিজকে মিউট কৰি আৰু ভিডিঅ' অফ কৰি ৰাখিলে আমাৰ অনুষ্ঠান প্ৰচাৰত সুবিধা হ'ব। মই এতিয়া বক্তৃতাটো দিবৰ কাৰণে ডক্টৰ অমল মেধিক আমন্ত্ৰণ জনাইছো। ধন্যবাদ।
ধন্যবাদ। মোৰ ভইচটো চাগে শুনিছে। ধন্যবাদ ডক্টৰ হিৰণ্যনাথ দা এণ্ড আৰু 15 মিনিট শিক্ষা এই প্লেটফৰ্মটোৰ লগত জড়িত সকলোকেইজনকে ধন্যবাদ জনাই আৰু this is my privilege to interact with the students in this platform. So I'm so very happy, and I wish the students are also they actively participate and they also interact with us. So that will be our success. Okay, with this, I'm going to start my video. So I'll share my screen first. Okay, I can. Okay, so I think my screen is visible now. Okay, so let me start. So this is the third and the last part of my talk on this topic, quantum physics up close. Okay, so before I begin, let me first quickly recap the part 1 and 2 of my talks. So in part 1, I basically started with saying that quantum particles behave in a way which is totally different from classical particles. And in fact, I showed some experiments to demonstrate that quantum particles show both particle and wave-like character. So they are not always particle, not always wave. Okay, so and this is very strange to our human experience, and we don't have an intuitive understanding of this behavior. However, I also mentioned that though we don't understand this behavior intuitively, we can explain this quantum phenomena by saying that there's a wave function associated with a particle, and the observations, experimental observations, can be understood on the basis of the wave function for the particle. And in part 2 of my talk, I mentioned that when we deal with particles of microscopic dimensions like electron, there is a fundamental limitation in our measurement process, and the limitation is that the position and momentum of a quantum particle cannot be measured simultaneously with absolute accuracy. So there's a principle, there's a Heisenberg's uncertainty principle, which says that so basically the uncertainty and in position and uncertainty in momentum, so they multiply to some number of the order of some constant h cross. So basically for quantum particle, we can't measure or we can't experience the position and momentum at the same time. Since we can't do that, so we cannot have a theory that talks about these two dynamical variables at the same instant of time. So, that means we can't use classical mechanics. So in this context, I also briefly mentioned the formalisms of classical mechanics, and there are several equivalent formulations, and all of them, we can use any of these formulations, and we can write the equations of motion for a classical particle, and we can predict, given the initial state of a classical particle, we can predict how it will move. So classical mechanics is predictive. So this is what I did in part 1 and 2. Today, to complete this talk, so I'll introduce the basic formalism of quantum mechanics. Okay. However, I will give only the heuristic ideas, and it will not be complete or comprehensive, just to make things very simple as possible. And we'll apply this formalism to a very simple problems and see what kind of motion this formalism of quantum mechanics give rise to. Okay. Yeah, so that's the idea, to give you a glimpse of how a quantum particle behaves in the simplest system. And since I'm discussing the formalism, so there'll be some mathematical equations which a general audience may not follow, but you need not worry about that. You'll still find it interesting to know the physics part, the conceptual aspect, and the phenomena part. So hope all of you can appreciate and will like it. Okay, so with this out of the way, so let me come to the formalism of quantum mechanics. Now, the formalism of quantum mechanics is given, can be started by a set of starting postulates or statement. So these postulates, I will state a few of the postulates in my own way. It will not be again comprehensive. And I will also compare the corresponding statement in classical mechanics, what classical mechanics says and what quantum mechanics says, so that this connection is more clearer and you can appreciate it more. Okay, so let me go ahead. So let's take this statement from classical mechanics. So classical mechanics, okay, so here the first statement is that the state or the dynamical state of a particle at a given instant of time t is specified by, or can be specified by, two variables. That is x, that represents position, and p is the momentum. So you specify x and p at a given time. So that specifies the state of a particle, dynamical state. Now the corresponding statement in quantum mechanics is this: the state of a particle at a given time t is specified by a wave function, okay, psi of xt. So, and this wave function is a complex number in general, but it's like a wave, that a wave or the wave function, it specifies the state of a particle here. Okay. Now, in classical mechanics, there's a special dynamical variable called Hamiltonian, which is defined as, or rather I call it a function, Hamiltonian function, which is defined as two terms, sum of two terms. So first term is the kinetic energy. It describes kinetic energy, and that's described potential energy. So this kinetic energy function and potential energy function, so these two is the Hamiltonian function. So, and this is a special function because it has physical significance, and we can write the equations of motion. So if we don't use Newtonian mechanics, alternatively, we can take this Hamiltonian function and also write the equations of motion of a particle. Okay, so that's the Hamiltonian. And so in quantum mechanics, the corresponding statement is that here we have a Hamiltonian operator. Okay, so what is done? So this function or this variable is converted or promoted to an operator in quantum mechanics. So this momentum or the kinetic energy is basically is the double derivative with respect to position. So it's a derivative operator. Okay, and this potential energy function is also considered as an operator, not as a function. So these two operator, if we add them, we get the Hamiltonian operator. So it also has the physical significance of total energy of a particle, like here in classical mechanics. So kinetic energy plus potential energy is total energy. So here this kinetic energy operator plus potential energy operator. So it basically can dig out information about total energy of a quantum particle. Okay, so the next statement in classical mechanics is that as I mentioned, x and p are state variable. So they define the state of a particle. So how the x and p changes with time t, okay, or in other words, how the particle will move with time t, that will be determined by this in the Hamiltonian formulation. It will be determined by these differential equations, okay, which is equivalent to Newtonian equations of motion. Okay, and in quantum mechanics, the corresponding statement is that the state of the particle, which is described by this wave function, so that is determined by this the so-called Schrodinger's wave equation, and and this is the central equation in quantum mechanics. So on the left-hand side, we have I h cross. Okay, I is the imaginary I, h cross is the constant, and I have time derivative of the wave function. So that is equated with this Hamiltonian operating. So this operating. So that's the terminology. We say that the Hamiltonian operates on the wave function. And so when we do this, whatever this operation, if we apply that operation, so this will basically give us a second order differential equation for the wave function. So, and we need to solve that to describe the particle. Okay, so that's for classical mechanics. So we find basically find x and p by solution of these equations, and here we find psi by solving this Schrodinger equation. And what is the physical interpretation of psi? So this is the physical interpretation. Psi mod square. So this quantity gives the probability that if we measure the position of the particle, then the probability to find a particle at the point x is psi mod square. So that's the probability to find a particle at position x and at time t. So it talks about probability. It doesn't talk about definite value. So similarly, if we make a measurement of momentum for the particle, what value we will get? So that also will be determined by psi, and similarly other quantities like energy and so on. Okay, so there are other postulates. It's this is by no means it is not complete. So to have a complete formalism, complete theory, there are other postulates are there, but I am skipping those. Okay. Okay, so with this, I will look at the Schrodinger's wave equations once more. And so this is the equation. If I expand the Hamiltonian operator, this is how it will look like. Okay, and so we will consider a case when this potential energy of the particle doesn't depend on time t. Okay, in general, it can depend on time t, but we'll take a simpler case when this potential energy doesn't depend on time t. It depends only on the position variable. In such cases, this wave function can immediately be factored into two parts. One is a function of position only, and the other is a function of time only. Okay. So as soon as we write this, we can also easily show that the position part of the function, wave function, it satisfies this second order differential equation. Okay. So that means we are after this wave function psi xt. We need to find out psi xt to be able to say anything about a quantum particle. And in the case when this potential is time independent, the time part is a known factor. The form is already, that function is already known. Only unknown part is the psi x part, and that part is calculated by solving this second order differential equation. So here's a mistake here. This should have been Vx, not T, and T is not here. Okay, so now we'll try to solve these equations for some simple problems. Okay. Okay, so the first example we'll take is the case of a free particle. Okay, a free particle is free. That means it is not under any external force. That's a free particle. So in classical mechanics, if we take a free particle, that free particle, if it is at rest, it will continue to be in rest. And if it is, say, moving with certain momentum and no external force, nothing, it's free, it will keep moving with that momentum. So that's the description of a free, that's how a free particle will behave in classical mechanics. Now here in quantum mechanics, so let us see. So since again, like I said, to know its motion, we have to write the Schrodinger equation, find the wave function. So we'll do that here. So it's a free particle, so no force, and so potential is 0. And so Schrodinger equation is becomes very simple. So it becomes these differential equations, which can be immediately solved. And we define a constant k like this, square root of 2m e by s cross square. And then a solution is of this equation is of this form. Okay, so some constant a exponential ikx. That's the space part of the wave function. Okay, so so this physically this function, it represents a plane wave that extends from minus infinity to plus infinity. That's kind of wave. I'll show the picture next. So that's the wave function for the particle. And this energy E, the E, constant E, which represents the energy of the particle, that is given in terms of k by this relation h cross square k square by 2m. Okay, and it is it can be shown that the significance of this number, if you multiply h cross and k, that this number physically represents momentum of the particle, right? So the energy of the free particle is p square by 2m, which is also the case for a classical particle. For a classical free particle, if it has momentum p, energy is p square by 2m. So here also the energy is p square by 2m. In that sense, these energy expressions are same for both this thing, but there are other differences. Okay, now this is if I picture that wave function at a given at a fixed time. So so is, I mean, it will look like this from a certain interval, but it extends from minus infinity to plus infinity. So okay, so that's the, yeah. If any, is there any question? Okay, I hope not. Okay, so this wave function, I'll interchangeably call it also a state. I mean, state or wave function will mean the same thing. So I'll say that in this state, if this quantum particle or the free particle exists in this state, in that case, so the momentum of the particle is well defined. So it's, in fact, there is no uncertainty in momentum. If we measure the momentum, if the particle is having that sort of wave function, and if we measure its momentum, we'll always find it to be equal to h cross into k. Of course, k can have any value that I'll come to later. So, so there is no uncertainty in P, so delta P is 0, and that's the Heisenberg's uncertainty relation. So from here, if we calculate the uncertainty in position x, so that will turn out to be infinite, right? So what does it mean? It means that the particle basically it can be found anywhere from minus infinity to plus infinity. Its position is totally undefined. Okay, so, and also it is very clear mathematically. It is very clear because the wave function, this function doesn't vanish anywhere. So there is a, since the psi mod square gives the probability to find a particle at a given point, and that psi, I mean that function is non-zero anywhere. So there is a probability to find a particle anywhere in space here. Okay, and so that's the space part or position part of the function. So if you multiply it by, with that time function, the time factor, so we get a complete wave function like this. And so this can be one more animation of this wave function is in this video. So I'll just show you. Also, this video also is taken from YouTube. So this free particle, it will show the wave function, that form of the wave function in an animated way, animation. Okay, so what's this?
In this scenario, we have a particle moving freely through space with a known momentum. However, the position of the particle is completely unknown because the amplitude of the wave function is the same everywhere. The square of the amplitude of the wave function at each location determines the probability of measuring the particle at that location. We can have some knowledge of the particle's location if the wave function consists of the...
Okay, so that's the wave function if we animate it. But please do not think that the particle, quantum particle, looks like a snake. Okay, so it's just a wave function pictured like that. Anyway, so I go. Okay, so the next, so few things I want to mention here. One is the quantization. Okay, what is quantization? Now, in this case, the free particle, as I showed, the total energy is in terms of this constant k, which is k is given by this relation. And if we look at the mathematically, if we look at that the Schrodinger equation or the differential equation, mathematically that equation is satisfied by that function for any value of k, any continuous value of k from minus infinity to plus infinity. Okay. And so which means that the energy of the particle, since it depends on k in this way, it can also have any value continuously between minus infinity to plus infinity. Okay, so then okay, so it's a continuous values of energy. So now you might wonder, the quantum mechanics. So by the name itself, quantum means it's something discrete, not continuous. So quantum mechanics means here things are quantized in generally. So you might wonder why in this case the energy is not quantized, it is continuous. Okay, so the answer is even in quantum mechanics things need not be quantized all the time. So these things get quantized only if a particle is forced, or it is confined in a finite volume of space. If it is unconfined, like in this case, it need not be quantized, so it's not quantized. Okay, and the second aspect is that this quantum particle can exist in different orbitals, different state. Okay, what do I mean by that? So this is the wave function I wrote for the free particle, and I say that this function represents a plane wave. So if the particle exists in this state, then the particle will have a well-defined momentum, but totally undefined position. Okay. However, it is also possible that the wave function of the particle is this in state is this. Okay, there'll be some constant. Okay, for the time being, ignore that. So let's say, I mean, basically it's a sum of two plane wave. One is with momentum or the wave vector k1, another with k2. So this is also possible state. That is also possible state. So this and then the sum of them is also a possible wave function or possible quantum state or possible avatar for the particle. Now, what is peculiar about this state? If you see, if the particle exists only in this state, and if you measure the position of a momentum of the particle, every time you will get the momentum equal to h cross k. Okay, that's precisely defined. Now particle can also exist in this state. So this wave function also satisfy the same Schrodinger equation. And in this state, if we measure the position, if we measure the momentum of the particle, 50% of the time we will find the momentum to be equal to h cross k1, and the other 50% of the time we will get the momentum h cross k2. So here we may get two possible momentum. Okay, I mean, say let's call this momentum h cross k1 p1, h cross k2 equal to p2. So if we make one measurement, we can get either of this p1 or p2 with 50% probability. Okay, so and if we again prepare the particle in the same state, that means say take I mean many particles, all of them in the same state. So first particle we make a measurement, we can get either p1 or p2. Second particle like that, p1 and p2. So if we keep many measurements on many different identical particles, so 50% of the time it will come out to be p1, and 50% of the time it will come out to be p2. Okay, so that's sort of the things that it implies. And also there is one more interesting case. So let's take only one particle, and the particle is in this state okay, and let's say we measure its momentum and find this momentum to be p1, that is h cross k1, that particle. So what happens is that after we make measurement, the process of measurement actually it affects this wave function. So after we make the measurement, the particle will no longer exist in this state. It will go to a state which is given by simply I mean exponential I k1x. So that means if we make a measurement, if we find the momentum of the particle to be p1, after making the measurement, it will affect the wave function, and the particle will exist in a state with momentum p1 only, with only momentum p1. That's the state. So it will no longer exist in a state like this, which is sum of two states. So the wave function collapses after making measurement. So very peculiar thing. Anyway, so let's go. So we can, in fact, here we have added only two components, but I can add infinite number of plane waves like this. Okay, so that infinite number of additions, so I have denoted it by integration. So that's like summing infinite number of plane wave, and it's with slightly different momentum, and we can choose these coefficients zk in such a way it's possible that the final wave function looks like this. So in this case, this kind of wave function is it goes close to a particle concept. You can see that. So this wave function is zero. I mean, only non-zero in this range. In this delta x, the wave function is non-zero. That means you will find a particle in this range somewhere. Beyond this, you will not find a particle. So because the wave function is zero. So basically, this wave function is now coming closer to describing a classical particle. So here the particle is localized. We say it's localized. So so it is a finite delta x. Delta x is not infinite in this case, and so see and to find this sort of state or this sort of wave function, we in fact mixed up many states with different momentum. So this momentum got mixed up now. And so now in this state, the particle will have neither well-defined momentum nor well-defined position. Okay. So, and then delta X and delta P will have will be of the order of H cross. Okay. So that is about same particle, different orbiters. Okay. Now next is now you can ask. So we can we see various particles. We see big particles, small particles, even smaller, and smallest particle. So out of these particles, which are classical particles and which are quantum? Okay. So now strictly speaking, all particles are quantum. So classical mechanics is only an approximation, and it is a very good approximation for a bigger size particle. So bigger is a qualitative word. So I'll show some numbers here. So one criteria that one can look at is the wave function associated with a particle. Also we call it matter wave. So that has a wavelength. Okay. So that lambda wavelength we can calculate that from if we know the momentum of the particle. So and also, or in other words, also from energy, either momentum or energy. So we can calculate that wavelength like this, wavelength of the matter wave. So now if we take an electron whose mass is of the order of 10 to the minus 13 kg, very small mass. We can't even imagine how small that would be. And if that electron is moving with a energy which is equivalent to 1 electron volt, okay, it's put in an electric field 1 volt per meter, it will accelerate, and so that electron will have a wavelength which is roughly like a nanometer. Okay, so the nanometer distance is very small, but still it is measurable, and it will have perceptible consequence to the things that human can measure. Now let's say, yeah, and now if we take instead dust particle whose mass also is very small, 10 to the minus 14 kg, but it's actually it's many times, several orders of magnitude heavier than the electron mass. So take the small dust particle, which is say moving randomly. Let's say its speed is 1 millimeter per second, and its wavelength will be 10 to the minus 16 meter. So minus 16 meter compared to 1 nanometer is several magnitudes, order of magnitude smaller, and it will not have any perceptible effect on anything that we can measure. So those kind of particle can be taken to be classical particle. So there is no hard boundary, but roughly we can estimate. Okay, so then so this is my first problem. Okay, now I move to the second example. Now here is a particle which is not completely free. It is confined to a box, a finite region. Okay. So, and for simplicity, we'll take a artificial one-dimensional box. Okay, so that means this particle can move here. move only left and right. That's the only degrees of freedom. But there is two hard wall. It cannot penetrate the hard wall. That's what we'll assume. And so we call it 1D box. And let's say L is the length of the box. So again, once we given this problem, immediately, the quantum mechanics students will have to write the Schrodinger equation. That means they'll immediately have to figure out what is the potential and write the Hamiltonian. So we'll do that. So the potential and function in this case, or potential energy in this case, is defined like this. So this V is within this box, it is 0. And at the boundary, it shoots up to infinity, and beyond this point, the potential is infinity, and there also is infinite. So that's the potential function here. And so now basically inside the box, the particle is free, no force, nothing. But as soon as it reaches the boundary, it has to come back because there is an infinite potential there. Okay, so now whatever wave function we find in this case, it cannot be like a plain wave function like in the previous case, because here the equation, so it means that the wave function it must vanish at the boundary. Wherever the potential is infinite, it must vanish there. Okay, so it will have a slightly different kind of wave function. So okay, fine. So we write this Schrodinger equation, and here we have to write a more general version of the solution of this equation, and that's the general solution. So when you write the solution, so A, B are constants which are unknown, and K is a constant which is given in terms of E like this. So that's the wave function, and like I mentioned, this function has to satisfy these boundary conditions. Okay, it has to finish at the boundary, and so we can, this is a small mathematical work. Okay, we can put that boundary conditions, and we'll find some equations, and those equations will determine what are the constants A and B. Okay, so but more importantly, those boundary conditions now will also dictate that K, okay, this number, K actually it's called wave number. So this wave number should now can have only these kind of values, which is n pi by L. N is an integer, 0 or positive, negative integer, it goes to 0 to infinity. So which means that this wave number or this K now cannot have continuous value, like unlike for the for the case of free particle. So now since it depends on this integer n, so n also in this case is called quantum number. So this is a problem where the quantum number is n, so it signifies different state of the particle. And so the energy also will depend on n, so En will be like this. So energy is also discrete now, is not continuous, so it's quantized. Okay, and so if we calculate the wave function itself, so it will be some simple functions like this, so cos and sine functions, okay, for different n. And we can picture this. So let's, for example, n equal to 1. So if we plot the wave function, it will look like this. So what is the meaning of this? So some things we can some few things we can immediately deduce from here. What we can deduce? The wave function is always 0 at the boundary. That means you will not find a particle there at the boundary. And at the central position, okay, the wave function is maximum. At the center of the box, it has maximum value. So the particle will span in this state. The particle exists in the state psi1. It will spend most of the time near the center of the box. So that's the that's what we can find. However, if the particle exists in this order, that means it exists in state psi2 instead, so it will have a wave function like this. And so you can see that at the center of the box, the wave function is 0. So I mean, so very, very peculiar. Now this the same particle, free particle, now it will not, in this order, it will not spend time near the center of the box. It will be somewhere, I mean, here and here you'll have maximum probability to find the particle. Okay, so and so on. We can so this will go to infinity. Okay. So this kind of, this sort of motion is there for a particle confined in a box. Okay, so it's totally different from the concept of a classical particle moving in a box. So if a classical particle, it will simply move here and there, bounce back here. If it's the elastic collision, again bounce back. So it will keep moving like this. But here, this is the situation. Okay, so now I move to another example where we'll examine whether we can trust physics. Okay, do you have trust in physics? So let's see. Okay, so in this time we'll take again. So we'll take a particle, but this time now a simple harmonic oscillator. Okay. So the example of a simple harmonic oscillator is a pendulum. So this is the pendulum where that ball, or it is also called pendulum bob. So it is pulled aside to some distance and release it, and it will keep oscillating. So For small oscillation, this motion is technically called simple harmonic motion. So for such a particle, again, so since as a physics student, so we'll have to look at the potential function for the particle. So in this case, the potential will depend on the displacement. So that's the central position. If we go away from the central position, so if the displacement is x, the potential will go by as square of x. So it's a kind of, it's a parabolic function. So that's the potential. And this is some case, some constants called spring constant. Okay, now so we can set up this. Now, if we, let's say we take this particle to be initially classical particle, so you can easily set up the equations of motion, and you can find how its position will vary with time t. And and if we release the particle, suppose we pull that particle to this point A and release it, and this is how it's this distance x is the distance from the center. This is how the distance will change with time t. So it's a cosine function of t. It will be oscillatory. So here at t equal to 0, it is at here. So as time goes, it will move this side. Okay, and it will go there and it will come back. It will keep oscillating. That's what this equation is saying. Okay. And we can also understand it intuitively. Our classical intuition, if we apply, also not even intuition. So there's a principle of conservation of energy. So it says that, so here at position A, it has this much of potential energy. So initially the ball was released from a rest. Okay, initially its velocity was, or speed was 0. Kinetic energy was initially 0, and that was the potential energy. So, and as we release it, as the ball moves here, so it acquires, so it gets some speed, so it gets some kinetic energy. So basically, and its potential energy decreases. So the potential energy get converted into kinetic energy. And here at the central position, it has maximum speed or maximum kinetic energy, 0 potential energy. And as it overshoots, it will go to this side. So its kinetic energy will get converted into potential energy. So its speed will reduce and reduce. And here the speed will become 0, because all of the kinetic energy get converted into potential energy, and it can go up to only this distance. Okay, it cannot overshoot these 2 points. So they are called turning points. These are turning points for the particle. They will not overshoot. Okay. So we can now, if we can trust this physics, then we can, one can do this experiment. So I'll show this very interesting YouTube video. So, okay, what's this?
I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works, and I'm still alive. See you Wednesday.
Okay, so now we'll see whether we can trust in the same way a quantum particle. Okay, so again, so I'm taking this now as a simple harmonic oscillator, but now it's a quantum particle. And again, immediately we have to write the, we know the potential energy function, so we'll have to immediately write the Hamiltonian and write the Schrodinger equation. That's the first task, and we solve this. Okay, and if we solve this, so we'll find what is this allowed values of energy. So it will be an expression like this. Okay, it will again depends on a quantum number n, which can have zero or positive integer. It cannot have negative value in this case. So 0, 1, 2, 3, infinity, and the energy. Allowed energy will be given by n plus half into this number s cross omega. So its energy is quantized again, can have discrete energy. And if we now write the wave function, so for simplicity, I'm assuming that these constants are all 1. So in this case, the wave function is of this form. So it has some constant a multiplied by an exponential exponential minus half x squared. Okay, multiplied by a function which is called Hermite polynomial, which will depend on the this quantum number n. Okay, so this sort of wave function we get. Now, if we plot this wave function, the red line is that, so this is the wave function for n equal to 0. By the way, n equal to 0 or is the lowest energy state, and the lowest energy state is also called ground state in general. So that's the ground state wave function. So in this wave function, what we see is that the wave function is maximum at the central position. So that means the probability or the particle will spend maximum amount of time near the central position, near the center. That's why it is 0, and it decays exponentially to 0 on both sides of the origin here, or the center. Okay. Now, what is different here? These two black line, or basically the point, this point here and that point. What is the significance of this point? Now, in the ground state, if you look at the expression for energy, so ground state means n equal to 0. The energy is half of h cross omega. So if we take a classical harmonic oscillator with the same total energy, that means with energy equal to half h cross omega, that classical harmonic oscillator or the classical particle would have oscillated between these 2 points only. So these 2 points are this and that point, they are the corresponding classical turning points. So particle would have turned back between these 2 points. And if we are doing the same experiment that I showed in the video, so probably we could have positioned ourselves somewhere here, and we would be very, very safe. Particle would not cross this point. Okay, but here now you can see that the wave function psi, so that is non-zero even beyond this classical turning point. So what does it mean? So since the wave function keeps the probability to find a particle at that point, so even if you take a point like this at distance 2, which is outside this classical turning point, so there also so if you are here, the particle, there is also a probability that you will find a particle here. That means if you are putting a detector here for the quantum particle, the quantum particle it will not return from here. It will cross this classical turning point and hit here, even hit up to there. That side also it will cross it. So it will tunnel the classical barrier, so to say, and it will move that side. And if we put a detector, it will hit the detector even there. Okay. So that's the now you can hopefully you can see there, right? So you can't trust physics, but not in classical way. So because you can see here what would have happened if that big ball would have tunneled through a barrier and then overshot the position. Okay. So the same situation, if we look at the another wave function now for n equal to 1, so these are wave function has different form, but this feature or this aspect is still there, that it is non-zero beyond these classical turning points, right? So here, this is the peculiarity of quantum particle. It can tunnel through barrier. It can tunnel through. Though there's a potential barrier, a classical particle would not have gone there, but a quantum particle can tunnel through. Okay, it can go to those spaces, right? So another wave function, and so on. Okay, so that's the that's this trust in physics. Okay, now I move to my last example, and then I'll finish my talk here. Okay. So can we have a quantum projectile? Okay, so I had shown the example of a classical projectile. So now it would be curious to probably you can ask this question, say like that classical particle trajectory, which was, I mean, the classical particle which was thrown from a certain height with a certain initial velocity. So I saw that it moved like that. So that's trajectory, and it hit the ground after some time. So that's what for a classical particle. Now, if we take a quantum particle like electron, and if we ask this question, so if that particle is released at a height 500 meters, say, with a speed 1 meter per second, and if you ask the question, nowadays quantum particle or the electron, how it will move, where it will fall on the ground. Okay, so now the answer is that the question itself is wrong. Why it is wrong? Because when you say that a quantum particle having position such and such and having speed such and such initially, so that cannot be defined. So the position and speed or position momentum at the same time cannot be determined precisely. So that statement itself is wrong. So we'll have to modify the statement, modify the question. So instead, we can say that let's say there is so this is a XY plane, and so this is the, I mean, kind of a picture of a initial state of the particle, which is a wave function like this. Okay, and then we can ask this question classical, I mean, quantum mechanically. So the question is this: if the particle, if at time t equal to 0, if the particle is at this point, we can ask what is the probability that the particle will be found at a certain other point at time t. That's the question we can ask in quantum mechanics. Okay, and the answer to that question, I mean, the first statement is that yes, so there will be there is some probability that the particle will be found here, and this electron or the quantum particle can move from here to here, okay, via any part. So I mean, this red part is basically actually I took the same part that the classical projectile took this part. So for the quantum particle also, it can take that part. Also, it can take any other part. So it can take part number 0, it can take part number 1. So it can move from here to here by part number 2. It can take this part, it can take that part, it can take infinite number of part. Okay, so it can take infinite, it can move, it can reach from here to here by taking infinite number of different parts. Okay, and quantum mechanics tells us this. So quantum mechanics gives a probability amplitude for each part. Given an arbitrary part from, say, point A to point B, okay, so the quantum mechanics tells us what is the probability that the particle will take that part, okay, and that probability is given by a complex number like this, exponential I s by h cross. H cross is the constant, and s is a quantity which is called action. So it's a quantity, it's a quantity defined in even classical mechanics. So that's the action for a part. So different part will have different action, okay, and it will have different probability amplitude, okay. And so if we want to know the net probability that the particle will reach here by following any of this part, so the net probability will be sum of the probability for all the paths. So that's what quantum mechanics will tell us. So this can be calculated for a given problem, and so that's the probability amplitude, and that's that z mod square. That's actually is the probability. Okay, so this is what the I mean basically I hopefully I hope I managed to give you a glimpse of or I managed to take you closer to quantum mechanics to see how quantum particles move. Okay, that was my endeavor, and hopefully I hope to have done it to some extent. Okay, shown you quantum mechanics to from some closeness. Okay, so with this I will finish my talk, and you can ask questions on this, and questions if you have, and some books I also mentioned before. So for students of physics who would like to know more about quantum mechanics can read can refer to these books. So, and once you are probably, I mean, once you want to know in more sufficient detail, more rigorous detail, I always suggest to go to this book. It's everything described in great details. Okay, and for general audience also, they can, I mean, so read these very interesting books on the development of the theory of quantum mechanics. Okay, and so this is my email address. So some students have some question, they can ask me, email me this email address, and also that's my phone number. Okay, so with this I finish my talk, and thank you for your attention. Okay, over to Hiranyada.
Thank you, Amal. Very nice. Before I go on to the question answer session, মই এটা কথা ঘোষণা কৰিব খুজিছো যে 21 ফেব্ৰুৱাৰীত আমাৰ এই 15 মিনিট শিক্ষাৰ এবছৰ সম্পূৰ্ণ হ'ব, আৰু এই এবছৰ উপলক্ষে আমি এটা প্ৰতিষ্ঠা দিৱস বক্তৃতা ৰাখিম, অনুষ্ঠান এটা ৰাখিম। তাত বক্তৃতা প্ৰদান কৰিব অসমৰ বিশিষ্ট লেখক ময়ূৰ বৰাদেৱে। তেওঁৰ বক্তৃতাৰ বিষয় হৈছে এক্সপেৰিমেন্টিং উইথ লাইফ। এই অনুষ্ঠানত ছাত্ৰ ছাত্ৰীসকল উপস্থিত থাকিব বুলি আশা কৰিলো, আৰু এই বক্তৃতাটোত তেখেতে বোধহয় তেখেতৰ জীৱনৰ যিটো যাত্ৰা, সেই যাত্ৰাৰ বিষয়ে কিছু কথা ক'ব, আৰু তেওঁৰ কলেজীয়া পৰ্যায়ৰ বা স্কুল পৰ্যায়ৰ শিক্ষাই তেওঁৰ জীৱনটো গঢ়াত কি ভূমিকা গ্ৰহণ কৰিছিল সেই বিষয়ে কিছু কথা ক'ব। আকৌ 15 মিনিট শিক্ষাৰ তৰফৰ পৰা ডক্টৰ অমল মেধিক কোৱান্টাম ফিজিক্সৰ ওপৰত এটা নহয় তিনিটাকৈ বক্তৃতা প্ৰদান কৰাৰ কাৰণে ধন্যবাদ জ্ঞাপন কৰিছো। আশা কৰো ছাত্ৰ ছাত্ৰীসকল ইয়াৰ দ্বাৰা উপকৃত হ'ব। আজিৰ এই অনুষ্ঠানটোত আমাৰ উপস্থিতি অলপ কম, বিভিন্ন কাৰণত হ'ব পাৰে। আজি আচলতে কেইবাটাও ঘটনা একেলগে ঘটিছে অসমত বিশেষকে, কিন্তু আশা কৰিছো আমাৰ যিটো এই ৰেকৰ্ডেড যিটো বক্তৃতা, সেই বক্তৃতাটো ছাত্ৰ ছাত্ৰীসকলে হয়তো পিছতো চোৱাৰ সুবিধা পাব, আৰু তেখেতৰ যোগাযোগৰ যিখিনি তথ্য তেখেতে ইতিমধ্যে দিছে, আমাৰ ছাত্ৰ ছাত্ৰীসকল তেখেতৰ লগত পোনপটীয়াকৈ যোগাযোগ কৰিব পাৰিব, বা 15 মিনিট শিক্ষাৰ জৰিয়তেও যোগাযোগ কৰিব পাৰিব। ইয়াকে কৈ মই যদি প্ৰশ্ন আছে বা কিবা মন্তব্য আছে, সেই মন্তব্য ৰাখিবৰ কাৰণে উপস্থিত থকা সকলক অনুৰোধ জনালো। নীলকমল।
মই কৈ দিছো বাৰু এটা প্ৰশ্ন মই দেখিছো পাৰ্থ শইকীয়াদেৱে কৰিছে প্ৰশ্নটো তেখেত যদি উপস্থিত আছে তেখেতে প্ৰশ্নটো নিজেই পঢ়ি দিলে ভাল হ'ব আপুনি আছে নেকি আপোনাৰ ভিডিঅ'টো অন কৰি দিব পাৰে
হয় মই
আপুনিয়ে পঢ়ি দিয়ক প্ৰশ্নটো কৈ দিয়ক সুধি দিয়ক
Thank you, Amal. It was a very nice lecture.
Okay, thank you.
I hope you remember me.
আপোনাৰ ভিডিঅ'টো অন কৰি দিয়ক যদি পাৰে
Okay, can you see me now?
Yeah, yes, yes. I'm
Okay.
video on here, sir.
Okay. Yeah, I have three general questions. The first question is you have talked about the wave function collapse. So, is there any extensive experimental evidence of wave function collapse, where people can show through experiment, at least at this time?
Oh, yes, it's of course. I mean, this all been. This is a very, very well established thing. It can be shown by experiment. Yes.
Exactly what kind of experiment they have done to prove?
Oh, no. It's you don't say in experiment. Okay, it's like in the talk I gave a picture of the wave function, some wave function, and in an experiment, say you cannot be looking at the wave function and we cannot watch the wave function collapsing. That's not what it is saying. So what is done is that the particle is in some wave function, some state, and you make any measurement, so any quantum measurement to determine. Let's say the wave function is such and such. So let's measure momentum of the particle. So initially it was not in a fixed momentum state. There's a probability to find different values of momentum, and we do the experiment and. We find that it has, let's say, has some certain momentum P naught. So an experiment has been performed. Any experiment that can determine a momentum, and the experiment throws up a value P naught for the particle. From then onwards, every measurement you make on the same particle, it will throw up the same value of momentum P naught. So the wave function is no longer the initial wave function. So it has reduced to it has collapsed to a state in which it has a fixed momentum.
Okay, so that means you have to make the measurement immediately, right? After doing the experiment.
Of course, if the particle is totally isolated, you can do measurement anytime. But if the particle, practically it cannot be isolated, there will be some, it will interact with something else, then it will again change the state. So that's a different matter. But for example, Stern-Garlick experiment is one experiment. You can see Stern-Garlick, no? So this electron spin. The electrons they have spin half. So initially the electron can either have the state plus half, minus half. So we shoot the electron beam through to magnetic field, inhomogeneous magnetic field. So it basically determines the spin. So some particles will be up. So it will separate the electrons in. So there will be original beam of electron. So this experiment, it will separate the electron beam into two different beams. In one beam, all the electrons will be having up spin only. In the other beam, the electron will have spin, which will be down. Now, if we put one more Stern-Garlick experiment on the one of these beam, let's say the beam with up spin electrons, now it will not split the electrons into two different beams because its spin has been down. It has collapsed to the state and it is having only spin up only. Assuming that in the meantime, the electron didn't get any chance to interact with its environment. So practically it will interact and it will change the state again. So, but that's a separate issue.
Okay. Okay, thank you. Now my second question was.
Okay, Amal. So the experimental quantum entanglement. So that can be cited as the evidence for the wave function collapse. Can it be?
Entanglement people of name, can you please repeat
entanglement যেটো experiment কৰা হৈছে যে measurement যেটো Einstein Podolsky he experiment. Now it has been done quantum mechanically. So the two particles are separated to an infinite distance. So their initial spin was 0. So if the spin of one particle is measured, then the spin of the other particle is automatically determined. So can it be, I'm just asking you, can it be cited as an experimental evidence for the wave function collapse?
এইটো এই এক্সপেৰিমেণ্টটো মই অলপ পাহৰিলো এইটো মই ইমিডিয়েটলি ক'ব নোৱাৰিম এতিয়া I mean this is slightly different thing involved here about the entanglement and what happens I mean if we take them to a infinite distance. So this case
I think that can also be cited as a function collapse experiment. Cannot see it. No. It is a complex. It exists only in the complex space.
Okay, so I immediately can't tell that. I forgot that what was the issue involved exactly there.
Okay, Patasakya, please go for your question.
Okay, the second question was like a very naive question. Like if you told about matter wave, but if I ask like what actually is waving in a matter wave, then what will be the answer?
There is no answer. So this no answer means no classical answer. Of course, there is answer.
Okay.
I mean, there is no. I mean, like I said, there is no classically intuitive answer. So it's a what is wavy is the probability amplitude. Okay, to find a particle that is waving.
Okay.
But again, that's an abstract quantity. Probability amplitude we don't experience. We experience only that psi mod square only. Okay.
Okay, my third question is like I'm actually teaching in undergraduate level, so we have a laboratory for quantum mechanics, a theoretical laboratory. So is there any software packages like in Python or MATLAB which can give you like the solution for Schrodinger equation in 1 dimension and also in 3 dimension?
Okay, so yes, I mean, of course it can. There is packages. So you are basically asking about what is called exact diagonalization. So you can exactly diagonalize any system. I mean,
okay.
So and there is, of course, there will be some software package, but it depends on what system exactly you are looking at. So it can give us. I mean, so but it can solve only a very simplest system. So for example, for a quantum particle, even if you have if you have non-interacting particles, you can easily solve. I mean, that's fine. It's a trivial kind of thing. But if you have that's also not very trivial. Of course, even for non-interacting, if the potential function Vx is arbitrary, you can't solve. I mean, this is a non-trivial still. But it depends on what kind of system. So if you have many degrees of freedom, so then basically. So, I mean, I'll tell you, so even if you take say maximum 40 particles which are interacting with each other, even with the biggest supercomputer in the world, we can't solve it because it's a limitation of the storage of information.
Okay.
But for some simple systems, of course, you will find some packages will be there.
Okay. Okay then, thank you.
Yeah, thanks.
আৰু প্ৰশ্ন আছে নেকি মই চাইছো 1 second Facebook আৰু YouTubeত মই দেখা নাই আমাৰ গ্ৰুপৰ ভিতৰত কাৰোবাৰ কিবা প্ৰশ্ন আছে নেকি স্যাৰ আপোনাৰ কিবা সুধিব লগা আছে নেকি
সুধিবলৈকে বিশেষ নাই কিন্তু মই এটাই কমেন্ট কৰিছো এইটো বৰ বিউটিফুল লেকচাৰ হৈছিলে অমলৰ এইটো কিন্তু আজি কিহৰ কাৰণে যেন ক'ব নোৱাৰো এই আজি ল'ৰা ছোৱালী অলপ কম মই কেইবাটাতো দিলো লতা মংগেশকাৰৰ গান শুনাৰ কাৰণে নেকি লতা মংগেশকাৰৰ গান কেউফালে চলি আছে প্ৰত্যেকটো চেনেলতে অসমৰ যিমানবিলাক চেনেল আছে সব চেনেলতে একদম লতা মংগেশকাৰৰ ওপৰত গান আৰু বিভিন্ন আলোচনা গতিকে সেইকাৰণে বস্তুটো অলপ কমিলে কিন্তু তথাপিতো আমাৰ যে ৰেকৰ্ড হৈ থাকিব ইমান খুটি নাতি মাৰি কথাবিলাক কৈছে অমলে সঁচাকে মই হৈছিল ল'ৰা ছোৱালী যিবিলাকে উপস্থিত নাথাকিলে তেওঁলোকে বহুত মিছ কৰিব কাৰণ কোৱান্টাম মেকানিক্স ময়ো বহুত দিন পঢ়াইছো কলেজত আণ্ডাৰ গ্ৰেজুৱেটো পঢ়াইছো পোষ্ট গ্ৰেজুৱেটো পঢ়াইছো বহুত বছৰ কিন্তু কিছুমান কথা মই অমলৰ লেকচাৰৰ পৰা মই দেখিছো যে এইবিলাক কথাটো মই কোৱা নাই ক'ব লাগিছিল তেনেকুৱা ধৰণৰ মোৰ
নহয় বাৰু ছাৰ বেছিকৈ কৈছে
নাই মই দেখিছো নাই কাৰণ প্ৰত্যেকৰ পৰা শিকিব লগা থাকেতো প্ৰত্যেকৰ পৰা শিকিব লগা থাকে
আৰু আপোনাৰ ভিডিঅ'টো অন কৰিব পাৰে যদি পাৰে
মোৰ ভিডিঅ'টো অন নাই নেকি
আচলতে
Okay.
হেৰি হৈছে নেকি পৰীক্ষা হৈ আছে যেন পাইছো মই কাৰণ
Still on live.
লাইভ আছে লাইভ
কি হৈছে
না লাইভ আছে
we can stop না ৰিফাত
ঠিক আছে তেতিয়াহ'লে মুনিমা তুমি কনক্লুজনটো কৰি দিয়া
ঠিক আছে
Okay. Amal Medhi, এই কোৱান্টাম মেকানিক্সৰ ওপৰত আজি যিটো 3 নম্বৰ লেকচাৰ আমি শুনিবলৈ পালো তাৰ কাৰণে তেখেতক বহুত বহুত ধন্যবাদ জনাইছো 15 মিনিট শিক্ষাৰ তৰফৰ পৰা আৰু আমি আশা ৰাখিছো তেখেতে ভৱিষ্যতলৈও আমাৰ লগত যোগাযোগ ৰাখিব আৰু আমি তেখেতৰ পৰা দিহা পৰামৰ্শ লৈ থাকিম আৰু আমাৰ ছাত্ৰ ছাত্ৰীসকলেও তেখেতৰ লগত যোগাযোগ কৰিব পাৰিব আৰু অকল কোৱান্টাম মেকানিক্স বুলি নহয় বিভিন্ন ধৰণৰ তেওঁ যিহেতু এখন ভাৰতবৰ্ষৰ এখন আগশাৰীৰ শিক্ষানুষ্ঠানৰ প্ৰবক্তা গতিকে তেওঁলোকৰ কেৰিয়াৰ সম্পৰ্কীয় কিছুমান কথা যদি জানিব লগা থাকে তেতিয়াও তেওঁৰ লগত সম্পৰ্ক কৰিব পাৰিব তাৰ কাৰণে তেখেতৰ ইমেইল এড্ৰেছটো সকলোৰে সুবিধাৰ্থে দিয়ে দিছে মই আশা ৰাখো আমাৰ ছাত্ৰ ছাত্ৰীসকলে সেই সুবিধাখিনি গ্ৰহণ কৰিব আৰু পুনৰবাৰ কমল মেধিলে আমাৰ 15 মিনিট শিক্ষাৰ তৰফৰ পৰা ধন্যবাদ জনালো আৰু লগতে ইতিমধ্যে আমাৰ ইয়াতে ঘোষণা কৰা হৈছে মঞ্চত যে অহা 20 ফেব্ৰুৱাৰী তাৰিখে আমাৰ 15 মিনিট শিক্ষাৰ এবছৰীয়া বৰ্ষপূৰ্তি উপলক্ষে আমি এটা আলোচনা চক্ৰ আয়োজন কৰিছো আৰু ইয়াত বিশিষ্ট অতিথি হিচাপে আমাৰ মাজত উপস্থিত থাকিব অসমৰ এজন বিশিষ্ট লেখক তেখেত ময়ূৰ বৰা তেখেতৰ নাম হয়তো বহুতে শুনিছে আমি আশা ৰাখিছো আমাৰ এই অনুষ্ঠানটিত উপস্থিত থাকি ছাত্ৰ ছাত্ৰী তথা শিক্ষক শিক্ষয়িত্ৰী আৰু অন্যান্য যিসকল আমাৰ শুভাকাংক্ষী আছে তেওঁলোকে আমাক উৎসাহিত কৰিব ধন্যবাদ সকলোলৈকে
ধন্যবাদ